So what's going on in this clip here is this is one of my first test runs of one after I built my Mark IV reactor. And what happens is once we put the plastic in there and we turn the microwaves on, shortly after the microwaves turn on, the plastic starts to immediately break down, right? But there's very few visual ways to know the plastic is breaking down because it's solid metal and steel, right? But the best way to know that the plastic is breaking down is we turn the plastic back into crude oil, like I said before, and a part of crude oil, it becomes a crude oil vapor, right? And that vapor can then be condensed to form our liquids, but there's some vapors that never condense, and those vapors end up being natural gas. So the end of the output of the machine, when it's turned on and the plastic is breaking down, is actually pretty much natural gas coming out. So I light the end of it because it's invisible. And if a flame starts and it sustains itself, that means natural gas is coming out. The plastic is being broken down. So that's what you see here in this clip.
Awesome. So basically, it's proof in the pudding. Basically, that everything's working.
Yeah, right. Now my next reactor I'm building, I'm gonna actually have some sight glasses in the pipes, so you guys should be able to literally see the liquids forming. It'll be really cool.
Nice. And correct me if I'm wrong, but you kind of explained it a little bit right now. But can you dummy explain it for? We'll say
Sure.
dummy explain it real quick about the process of how pyrolysis happens with your microwaves.
Sure. So in pyrolysis, microwave pyrolysis, well, I'll say this to begin with. So what is the difference between pyrolysis and microwave pyrolysis? Microwave pyrolysis utilizes microwaves. Traditional pyrolysis, or just regular pyrolysis, utilizes a flame. So how does pyrolysis work? We take a container that's airtight, meaning no air is able to get into this container. We load the plastic in. We have to then apply heat to the container to heat up the plastic. Traditional pyrolysis applies heat through a flame. So you burn wood or a natural gas or propane under it, and then it heats up the container. But let's think about it. In order to do that, the flame has to go from the actual source of the fire through the air to the bottom of the container. Then it has to conduct to the inside of the container, from the inside of the container to the plastic, and then the plastic then has to conduct that heat to the rest of the plastic inside. There's so many heat transfers in that alone that you're going to lose a ton of your energy and a lot of time. Microwave pyrolysis differs. It's just like this. Hot pocket in your oven takes 15-20 minutes. Hot pocket in your microwave oven, less than 5 minutes. Why? Because microwaves operate off of what we call volumetric heating. That is when you heat from the inside out rather than the outside in. So incorporating microwaves into pyrolysis, using microwaves to heat up the plastic, we don't even have to heat up the container anymore or the air. We don't have to burn anything anymore. We literally can just turn the microwaves on. They heat up the plastic directly, go right to where you want it to heat. And that vastly boosts the efficiency, how quick it happens, how much energy it takes to do the process. So I originally started building regular pyrolysis machines, but I moved to microwaves because I knew that in order for this to be at a scale that we can use in the world, it needs to be efficient. And the best way to do that was microwaves. So going off of that point, microwave pyrolysis, same thing, airtight container, microwaves come in, plastics in, microwaves hit the plastic. The plastic cannot burn because there's no oxygen. Without oxygen, a fire cannot start. Without a fire, there's no smoke, something does not burn. So instead of it burning, the microwaves heat it up and it turns into a liquid. That liquid is then broken through a permanent chemical change under heat again into a vapor. When that plastic is now vapor, it is no longer plastic. It is returned into crude oil because the molecular chains that made it plastic, the long chains, have been split apart by heat to form vapor. So now that vapor is crude oil vapor. Okay? So that vapor is warm and hot. It needs to be returned to liquid through condensation. What is condensation? Condensation is when you cool down a vapor and turn it into a liquid. It's exactly what water does as clouds. So water starts as water. The sun heats it up. Steam goes up. Clouds rain. We get the water come down. We have to do essentially the same thing here. So we turned the plastic into crude oil vapor. Now that crude oil vapor goes through a condenser to then condense the liquids out and get it back into the liquid form of crude oil. Okay. And after that point, now when we cool it down, it's no longer plastic again, like I said. So when it cools down, it's not turning this vapor back into solid plastic. it's now turning it back into liquid crude oil, because when it becomes that vapor, it's a permanent chemical change. No plastics exist. That vapor can only exist through the absolute chemical and physical destruction of the plastic's hydrocarbon bonds. So that is also why when we make these fuels, there are no microplastics, there are no plastics in these fuels, because the fuels can only exist through the plastic's complete destruction. But there's some vapors that never condense, that never turn into liquid. There's some vapors that stay vapors forever. Since those vapors are crude oil vapors, once again, well, guess what one of the byproducts of crude oil is? Propane, natural gas, flammable gases, pretty much fuel gases, gaseous products. We collect those gaseous products because those gaseous products are fuels. So we collect the oils, we collect the gaseous products, but what's left of the plastic in the machine? Well, all that's left of the plastic in the machine is pure carbon and minerals. And the reason why is because anything organic in there, anything that has organic molecules, right, that can be broken apart by heat, they all get destroyed because the heat is too much for anything organic to remain intact. So all those become the fuels, and we have solid carbon in the end that comes out at the end of the plastic. That carbon can be used as biochar, can be used as pigment, road filler, can be put in cement. It has tons of uses. So going through all that I just said, if you noticed, I didn't mention any emissions or waste. And that's because there are no emissions of this machine, because every single product that we get, we don't want to emit because it's useful. Our fuels, our gaseous fuels, our carbon, all of those things have monetary value. The byproducts, the waste products of this machine are literally the fuels.
Awesome. And basically, the way you've pioneered in this pyrolysis industry is by you using microwaves instead of direct heat, correct?
Right.
Congratulations on that concept and idea and vision.
And I will make this clear. I was not the first to use microwaves. There are a ton of research papers on microwave pyrolysis. However, studying microwave pyrolysis, I learned the reason why it isn't done, even though it's so much more efficient. And the reason why is it has been extremely difficult to design a machine that uses microwaves, but also can be made continuous and scalable. When I read my research papers on microwave pyrolysis, all of these microwave pyrolysis research papers were done with really small lab scale microwave pyrolysis machines. You know, expensive they make these scientific microwaves called lab microwaves that are specifically designed for experiments like this, and they're expensive, right? But when I wanted to build one myself at home, I didn't have that luxury of getting one of those. I had to build it myself. So in me having to build it myself, I actually, I guess you could say, just accidentally discovered a way how to make it utilize microwaves, but also be scalable and continuous, because I just kept improving my own process, having to figure out how to build it at home. Because when I was looking to build regular pyrolysis, right, I found guides online. I found my first reactor that I designed off of Instructables. But when I dwelled into microwave pyrolysis, when I was looking online, there were literally only research papers with no pictures. So I had to completely design my own microwave pyrolysis reactor from scratch. And in continuing to improve my design and learning how it could be made better, I eventually came up with certain design aspects that allowed it to actually solve the problems that had kept this technology from scaling up like it needed to from the beginning. So ironically, it was my lack of resources that allowed me to come up with the innovation necessary for this whole industry. Because if I had the lab scale equipment and the lab scale microwaves, I may never have, out of, I guess you could say, necessity of the survival of my own machine, came up with what was necessary to allow it to be done continuously and scalable.